Hello, everyone. Welcome back to this week's algebraic graph theory seminar. This week, Sam is going to talk about edge domination in incidence graphs.
Okay, thank you, Tina. Yes, so the title of the talk is Edge Domination in Incidence Graphs. This is joint work with Sam Spiro and Sam Adriaensen. So this is our joint SAM paper. You may think that it's 3 SAMs, but actually it's 4 SAMs because you might notice that our last names here are not in alphabetical order, and that's because if you plug in my name here in the middle, then you have an extra Sam here popping up. So this was some sort of cosmic coincidence that we could not be. So anyway, the Sam paper, Edge Domination in Incidence Graphs. So let us start with a little bit of introduction. It's a bit of graph theory and a bit of incidence geometry. So what is an incidence structure? Let us first define this. Very basic. You have a tuple, 2 sets P and B, where the elements of P are called points. The elements of B are called blocks. And we will use the convention that any block is just a subset of points. Right, okay. So very easy thing, just a pair of points and a pair of blocks, which are subsets of the points. Now, the nice incidence structures are the one which satisfy some regularity conditions. And we will be looking at designs. So by a VK lambda design, I mean an incidence structure that satisfies the following properties. The number of points is equal to V. Any block contains K points. And if you take 2 distinct points, then there are exactly lambda blocks containing both of these points. Right, so you just take 2 points, you count all the blocks containing these 2 points will always be equal to lambda. And then we have the inequality by Fisher, who tells us that the number of blocks will always be at least equal to the number of points. And in case we have equality, we call this a symmetric design. And the nice thing about the symmetric design is that now you can interchange the role of points and blocks. And you get, again, a design with exactly the same parameters. So if the number of blocks equals V, then you can flip the role here. So we have that any block contains K points. If you flip it, then this means that any point lies in K blocks. And we also have that if you take 2 distinct points, then they lie together in exactly lambda blocks. So this means that if you take 2 blocks, V1 and V2, and they are distinct, then they share exactly lambda points. These are very nice incidence structures. Okay, so we have these incidence structures. Let's make some graphs out of them. The incidence graph of an incidence structure looks as follows. It's a bipartite graph. One of your bipartition classes is the set of points. One of your bipartition classes is a set of blocks. And then you have that a point P is adjacent to a block B if and only if they are incident. So if and only if the point P is contained in the block B. Okay. And in these graphs, you can start studying different sorts of graph parameters. One thing you can study are dominating sets. So what's a dominating set? In a graph G, well, it's a subset of the vertices such that any any vertex you take in your graph lies at distance at most one of this set. So there will always exist some vertex in your dominating set such that the distance in your graph between V and S is at most 1. So if you make a drawing, then this means the following. You have your graph G, you choose some vertices in your graph, and then any vertex V you take will always be adjacent to one of these vertices in S, or will be itself in S. And if you have a dominating set, well, if you enlarge it, so if you go to a superset, it will still be a dominating set. So the interesting question is the ones which are small. In particular, we're interested in the size and structure of the smallest ones. Now, if you investigate this problem in the context of incidence graphs, if you want a small dominating set, this means you take a small number of points and a small number of blocks. And now you want that every block outside of your dominating set is incident with a point in it, and vice versa. Every point outside your dominating set is to be incident with a block in it. So especially this means if you look at the points inside your dominating set, they have to be well, they have to intersect almost every block in your incidence system. They're allowed to only miss a few blocks. And if you make this definition a bit more strict, if you go to a set of points that does intersect every block of your incidence system, then this is called the blocking set, and these are very well studied objects. So investigating dominating sets in incidence graphs is very much linked to investigating blocking sets and their duals called covers. And this is a well-studied problem. So this has been studied in general in incidence graphs of designs. Hager and Notch proved the stability result in the incidence graphs of projective planes, where they really proved that the only small dominating sets you can make arise from blocking sets and their duals. Hager and Hernandez Lucas also investigated this in generalized quadrangles. So this is a well-studied problem. And this is not exactly what we're going to be looking at today. We'll be looking at a related problem, namely edge dominating sets. There are different ways to define an edge dominating set. Again, we're working in a graph G. Now we're going to take a subset S of the edges, and it can satisfy any one of these properties. They are equivalent. Either you can say that it's a dominating set in the line graph, of G. So this means that any edge is at distance at most 1 of S. This means that any edge is either contained in S, or there is another edge. If you take an edge E, there will always be another edge which shares at least one vertex with E. So another way to define this is for any edge in E, there exists an edge in your edge dominating set such that S and E are not disjoint to each other. And a third way you can define this is as follows. If you look in your graph, you have your edge dominating set. So you choose some edges in your graph. then you can now look at the vertices which are not covered by the edges in S. Then these uncovered vertices cannot contain an edge, because if they would contain an edge, then this edge does not intersect any edge in your edge dominating set, which contradicts the definition. So a third way to define this is that the vertices which are not in the union of S are a co-clique in your graph. And the question is, again, what is the size and the structure of the smallest edge dominating sets? And we will use the notation gamma E. So the gamma is often used for the size of the smallest dominating set, and then we add a little index E to emphasize that it's now the edge domination number that we're looking at. So this is the size of the smallest edge dominating set. And there is an interesting observation by Yanakakis and Gavril. They gave a sort of procedure where if you start from an edge dominating set of smallest possible size, you can always transform it into a matching of the same size. So you can always assume, if you're looking at the size of the smallest edge dominating sets, that you're looking at sets of edges which are pairwise disjoint. So this is a nice thing to know, because we know a lot of things about the existence of matchings in certain graphs. Okay, so now if you look at the definition of an edge dominating set in an incidence graph, and one of the definitions was that you have here your points and your blocks, and then you have some edges between them. And if you look at the uncovered vertices, then they are a co-clique in your graph. If you start to study these edge dominating sets from this perspective, then if the number of points and blocks are very far from each other, the problem becomes quite trivial. If the number of blocks is very large compared to the number of points, then the edge domination number will be either the number of points or maybe the number of points minus one, but it's quite trivial to study it in those cases. So we will look not at the case where they are far apart, but the other extremal case, namely the case where P and B have the same size. So in other words, since we want some structure on our graph, we will be investigating it in the context of symmetric design. And so if you have an edge dominating set of smallest possible size, we can assume that it's a matching. So it covers the same number of points as the number of blocks. And since the size of P equals the size of B, this means that the number of uncovered points equals the number of uncovered blocks. And the fact that we have an edge dominating set means that these uncovered points and blocks are a co-clique. So in other words, no point uncovered by my edge dominating set is incident with or contained in an uncovered block. And this gives us the definition of an equinumerous incidence-free pair. So this is defined in symmetric designs. As a pair XY where the size of x equals the size of y. They're equinumerous. X is a subset of the points, y is a subset of the blocks, and a no point of x is incident with or contained in, same thing, a block of y. And so the thing we know is that an edge dominating set gives rise to an equinumerous incidence-free pair. So I will abbreviate it as EIFP because otherwise it's quite long to write it in full. So anyway, yeah, an edge dominating set gives rise to an equinumerous incidence-free pair, which is nice because these things, well, we can study them with known techniques and known structures of certain symmetric designs. So we can certainly use these equinumerous incidence-free pairs to give some interesting bounds on the size of an edge dominating set. You can wonder if the converse also holds. If you have an equinumerous incidence-free pair, can you always use it to make an edge dominating set? So what this means that you start in your graph by taking some equinumerous incidence-free pair, and you're wondering if you now remove these vertices from your graph, does your graph allow for a perfect matching? And we know how we can test this. This is Hall's theorem. And we will use a bit of a strengthening of the theorem by Ehrenborg. So let's say that we have a bipartite graph with bipartition classes L and R. And let's suppose that both bipartition classes have the same size, because in our case this holds. Then G admits a perfect matching if and only if for any subset S of L R of R, so a subset of one of the bipartition classes, and this is the strengthening by Ehrenborg, you can assume that the size of S is at most half the number of vertices in one of these classes, rounded up. Then the neighborhood of S needs to contain at least as many points as S. So this is Hall's condition. Okay, so now what we want to do is go to our incidence graph. We remove this equinumerous incidence-free pair, and then we want to check if the induced subgraph that we're left with satisfies Hall's condition. So in particular, this means that if you take, well, let me maybe make the sketch over here. If you take a subset S of points over here, which is not too large, then you want to look at its neighborhood in the induced subgraph. So if you look in the entire incidence graph, yeah, its neighborhood lives over here and a little bit in the vertices of your equinumerous incidence-free pair. You want to prove that this is large enough, right? So especially this part has to contain at least as many vertices as there are in S. How can you prove this? Well, if you look at the incidence graph of a design, it satisfies some nice expanding properties. And if you take two vertices in one of the bipartition classes, so let's say 2 points, then you know exactly how many common neighbors they have. This is exactly equal to lambda. And you can use this to give some nice bounds on, that prove that your graph is expanding, in the sense that if you take some subset S, then its neighborhood will be large enough. And one way to quantify this is using the Kováry-Seuss-Turan theorem. So if you apply this to the incidence graph of a symmetric design. Then if you take a subset S of the points and a subset T of the blocks, then the number of edges between these two sets will be at most square root lambda times the size of S minus 1 times square root size T plus the size of T. And since this holds in the incidence graph, it holds in all of the subgraphs of the incidence graph. So you can really use this theorem to give a lower bound on the size of a neighborhood of a set in any induced subgraph of your incidence graph. And if you start quantifying this, then you will notice that you can now check Hall's condition in the induced incidence graph you're left with here. If S is not very small, if S is really small, then you need a bit of other very elementary counting arguments. But essentially, if you combine these two theorems, so Hall's theorem and the Kováry-Seusteran theorem, then it comes quite naturally to prove that, well, this is the main theorem of our paper, that any equinumerous incidence-free pair gives rise to an edge-dominating set. So let me write down the exact statement. In a symmetric pk lambda design, and we have a condition here that k is at least 100. It's not very restrictive because there's only a finite number of symmetric designs where your block size is at most 100. And we're interested in the asymptotics anyway, so if you lose a handful of designs, it's not so bad. You can optimize this bound. Anyway, if you assume this, then every equinumerous incidence-free pair gives rise to an edge-dominating set. And so, in particular, this means that gamma A equals V minus the size of the largest equinumerous incidence-free pair. When I say the size of such a pair, I mean the size of one of its two components. So they are the same anyway, so it doesn't matter whether you choose the points or the blocks. Okay, so this is nice because now you know that you can both get upper bounds and lower bounds on the edge domination number by studying the equinumerous incidence-free pairs. So let us start by looking at the lower bounds. There's a proposition by Willem Hamers which characterizes the lowest possible, the largest possible equinumerous incidence-free pairs. And because if you want a lower bound on your edge domination number, then you want an upper bound on the size of an equinumerous incidence-free pair. And they are attained by what's called the maximal arcs. So if you look at a maximal arc in a symmetric VK lambda design, this is a set of points such that any block intersects it either in 0 points or in n points for some integer n. And this n is called the order of the maximal arc. An interesting thing about these maximal arcs is you can now look at the set T of all the blocks which intersect your arc in 0 points. So just blocks disjoint to your arc. And then they are a maximal arc in the dual design. So this means that if you take a point, then it lies in either 0 or the order of the dual arc is k minus lambda over n blocks of T. And the points lying in 0 blocks are, of course, the points of S themselves. And every other block, it's a straightforward counting exercise. Sorry, every other point, I mean, every point outside of S will lie in exactly k minus lambda over n of these blocks. So yeah, when are these two arcs of the same size? Well, that's when their orders are equal to each other. So we want that n is equal to k minus lambda over n, or in other words, n needs to be the square root of k minus lambda. And this gives us the proposition by Willem Hamers, which says that if xy is an equinumerous incidence-free pair in a symmetric VK lambda design, then the size of x is at most the size of a maximal arc of order square root of k minus lambda. So what is the size of this arc? You can count it quite easily. You start with 1 point. There are k blocks through this point, and each of these blocks will contain exactly the order, so root k minus lambda minus 1 extra points of your arc, so that they contain square root of k minus lambda total. But now if you fix 2 points, the number of blocks through these 2 points equals lambda. So any point outside, except for the one that you fixed, you counted it lambda times, so you need to divide by the factor of lambda. And this is the size of a maximal arc of order square root k minus lambda. And so equality holds even only if x is a maximal arc of order square root k minus lambda, and y is its dual arc. So by dual arc, I mean just all the blocks missing x, and we know this is again a maximal arc in the dual design. So if you're familiar with the work of Willem Hamers, then you probably know how he proved this. He did it with interlacing of eigenvalues. Yeah, basically he used what we would now call the expander mixing lemma. But you can also prove this theorem with elementary counting techniques. So they're what's called the standard equations, or the variance trick. Pretty elementary stuff will also give you the same result. So now we have a nice lower bound on our edge domination number, or a nice upper bound on the size of equinumerous incidence-free pairs. Now let's say that this bound is approximately k root k divided by lambda. So we have an idea of which order of magnitude we expect the size of equinumerous incidence-free pairs to be. So now that we have this bound, we can look at some constructions and see how close we can get to this order of magnitude, k root k divided by lambda. And let us start with everybody's favorite example of symmetric designs, the projective planes. So these are the designs, the symmetric designs where lambda equals 1. And then they are necessarily, their parameters are of the form q squared plus q plus 1, q plus 1, and 1. So the classical construction of a projective plane, so the PG2Q construction, you obtain this by taking a finite field, FQ, building a three-dimensional subspace over it, or three-dimensional vector space over it, and then as points, you take all the one-dimensional subspaces of your vector space, and as blocks, you take the two-dimensional subspaces. Okay. So if you look in these projective planes, you might wonder, how can we make large equinumerous incidence-free pairs? And especially, do maximal arcs of order square root of k minus lambda, which is in this case square root of q, exist? We know exactly when they exist in the classical projective planes. So of course, for such a maximal arc to exist, we need that the square root of q is an integer, so q needs to be square. Then Denniston proved that if q is even, we can always make such a maximal arc. But I mean, if q is even, and of course is square. But Simeon Ball, Art Blockhaus, and Franco Manzocca, they proved in the 90s, after well, the conjecture was open for some decades, that if q is odd, then the only maximal arcs in PG2Q are trivial examples. So either a point, empty set, or the complement of a line, but you can do nothing non-trivial. So if you put these results together, then we know that, say, PG2Q contains a maximal arc order square root of q, even only if q is an even square. Interesting to note here is that there are other examples of projective planes, and one of these are the Lüneburg planes, and Jeff Tass proved there that they also admit maximal arcs of order square root of q. So in the non-classical case, there are still some planes which admit these arcs. And so now in this case, we know exactly what the edge domination number of that incidence graph is. And also we know what the edge dominating sets of minimal size look like. The only possible way you can construct them is by starting from a maximal arc of order root q, taking this arc and its dual arc, removing it from your incidence graph, and then make a perfect matching in the graph that's left over. But of course, this doesn't answer the question in case that q is odd or q is non-square. But in those cases, there are some nice constructions, and they use the concept of a polarity. So what is a polarity? Can define it again in a symmetric design. It's a map rho, which maps points to blocks and blocks to points. Such that it preserves incidence. So if you take a point P and it lies in a block B, even only if rho reverses the inclusion. So the image of your block under rho has to be contained in the image of your point under the polarity. And you always you also assume that the row is an involution. So if you apply it twice, then you just have the identity. And now you can look in the polarity graph. So this is the graph defined on the points of your symmetric design. Where the edges consist of the pairs of points P and R, such that P is contained in R to the row. And the nice thing about the polarity is that, and this holds even only if P to if and only if R to the row squared, which is of course just R, is contained in P to the row. So this is a symmetric graph. And if you have a point P, which is contained in its image on the row, then we will put a loop on it in the graph. So it's not necessarily a simple graph, it can contain loops. But the nice thing now is if you take a co-clique in your polarity graph, right, then you have a set of points and you can look at their images under the polarity. There will be no incidences between them, right? Because if you take 2 points P and R of your co-clique, then P is never incident with R to the row. So if you interpret this, your co-clique as a set of points and as a set of blocks, it's an equinumerous incidence-free pair. And the size of the co-cliques in this polarity graph have been investigated in different papers, one by Williford, one by one of my co-authors, Sam Adriaensen, together with Pavese and Storme. And so they prove that always you can get close to let's say the optimal construction, which is maximal arc of order root Q. So if you again look at the bound we had here, we know that the upper bound on the size of an equinumerous incidence-free pair is around K times square root K over lambda. So in our case, this is approximately Q root Q divided by 1. And so what they proved is that the size of a co-clique, the maximum size of a co-clique in your incidence graph is always of the order a constant minus some lower order terms times Q square root Q. Where this constant is at least 0.19 if Q is odd and non-square, and then in the other cases the constant is a bit better. But so anyway, there always exist equinumerous incidence-free pairs of this size. So let's say roughly 1/5 times K square root of K. It's already the correct order of magnitude. The only question that remains is what is the optimal constant that you can put here. These are nice constructions, very close to the optimal possible one. Okay, so that's what we know in the projective planes. We also looked at some other designs. There are some very nice constructions of Hadamard designs. One of the constructions is from the Paley matrices. And so in this case, your Hadamard design looks as follows. It's let me check. Yeah, a 2Q plus 1 Q and Q minus 1 over 2 design, where Q is a prime power equivalent to 1 mod 4. And how do you make this design? Well, the points of your design consist of 2 copies of the finite field of order Q. and an extra point at infinity. And there's a polarity in your design, so you can use this to define the blocks. For this, we will define the quadratic character. So the quadratic character on your finite field FQ maps any element to 0 or plus or minus 1. And it will map some element x to 0 if x equals 0, to 1 if x non-zero is a square, and minus 1 if x is not a square. Okay, so then we get a polarity in our Hadamard design, and it will map the point of the form x1 to the block consisting of the points y epsilon, such that the quadratic character of x minus epsilon is equal to 1. So x minus epsilon is a square. Plus it also contains itself. If you have a block of the form x minus 1, then you map it to all the points y epsilon such that x minus y is a square even only if epsilon is 1, and a non-square even only if epsilon is minus 1, and you also add the point at infinity. And lastly, the point at infinity is just mapped to FQ union, FQ not union, but times minus 1. Okay, so now we have this design, which is quite nice. It has a lot of symmetry, and it also admits a polarity. So we can do the same thing as we did before and look in the polarity graph of our design and try to find a large co-clique in there. So yeah, one question you can wonder is, what is the upper bound on the size of equinumerous incidence-free pairs? So generally this is k times square root of k divided by lambda. So in our case, this is roughly q times square root of q divided by q over 2. So this is, well, the upper bound will be roughly 2 times the square root of q. Now, if you look in the polarity graph, if you take a point of the form x1, it will always be adjacent to itself because x1 is contained in its image under the polarity. So here you will have a loop, and therefore it can never occur in a co-clique. So this is not very interesting. And the only points that are left to construct co-cliques from are the x minus 1 points and infinity. But the point infinity is adjacent to all these other points. So also, this is not very helpful. If you take your point at infinity and you want to make a co-clique, you can't add any other vertex. So we're interested in the points of the form x minus 1. And when are two of these points, x minus 1 and y minus 1, not adjacent in your graph? Exactly when chi of x minus I equals plus 1. But then if you go look in your classical Paley graph, this means that the co-cliques in the polarity graph just correspond to the cliques in the Paley graph. And they have been studied a lot, especially if Q is square. Then we know exactly what the cliques of maximal size are in the Paley graph. This is what Aart Blok has proved. They are translates of cosets of FQ, of F square root of Q, so of the largest subfields of FQ. So this means that if Q is square. Then the polarity graph has coccyx of size square root of q. So this is nice because we see again that this is the correct order of magnitude. And we know that there exist equinumerous incidence-free pairs of size square root of q, and the upper bound we have is 2 times square root of q. So the order of magnitude is correct. It's just a matter of optimizing the constant here. And I will very briefly mention some other designs coming from Hadamard matrices, which are called coming from symmetric Bush-type Hadamard matrices. They have these parameters. So for some integer a, it's 4 times h squared, 2h squared minus h, and h squared minus h. And this means that if you now look at the square root of k minus lambda is exactly equal to h, but the points and the blocks are partitioned into maximal arcs of this order. There are some nice constructions of these types of designs, and we see that they have the maximal arcs of the correct order. So again, here you know exactly what the edge domination number of their incidence graph will be. Yeah, so I see I'm running a bit out of time, so I'm going to very briefly mention the semi-biplanes, but let me just go directly to the construction. So if you look at symmetric designs where lambda equals 2, we don't know a lot of them. I think probably the known constructions, maybe there are between 10 and 20 of such designs, but at least a finite number and quite small. So the next best thing is called semi-biplanes, where you allow that if you take 2 points, they're not necessarily contained in 2 blocks. They're also allowed to be contained in 0 blocks. Now, if you look at the Hamming graph, so this means you take a graph G, where your vertices are binary vectors of a certain length n, and your edges consist of pairs of vectors x and y, such that there exists a unique position I, where xi and yi are different. This is a bipartite graph, right? Because you can define the weight of any vector as its Hamming distance from the 0 vector, so just the number of positions I, such that xi is different from 0. And if you take a vector of even weight, it's only adjacent to vectors of odd weight and vice versa. So this gives you a bipartite graph. And you can interpret this as the incidence graph of some incidence structure. And it's not that far from being a symmetric design. So we get this semi-biplane, 2 points are adjacent with either 2 blocks or 0 blocks. But if you look in this incidence structure, then the theorem that any equinumerous incidence-free pair gives rise to an edge-dominating set doesn't hold anymore, because you can look at the points. Let's say we identify the points as the vectors of even weight and the blocks as the vectors of odd weight. Now, if you take the points of, let's say, x is the subset of points where the weight of this point is at the most n over 2 minus 1, and I take as y the blocks whose weight is at least n over 2 plus 1. So then these are the even vectors of small weight and odd vectors of large weight. This is an equinumerous incidence-free pair. But the problem is that it will not give rise to an edge dominating set, because if I take a point X and the weight of this point is large, so in the extremal case it's n or n-1, depending on whichever of these is even, then of course all its neighbors will be contained in the set Y. So if you look in the incidence graph, we remove the points of small weight and the blocks of large weight. So any point of small weight, any point of large weight, you deleted all of its neighbors in this graph. And of course, you can not make a matching anymore in the graph you're left with. So this really shows that to have this theorem, to go from equinumerous incidence-free pairs to edge-dominating sets, you need some nice expanding properties of the incidence graph of your incidence structure. And I would like to end my talk by giving a little bit of an advertisement for the summer school we're organizing in September in our university in Brussels. So it might also be interesting for people interested in algebraic graph theory, because we have Kristal Guo who will be talking about quantum walks on graphs from association schemes. Valentina Pepe is also an expert in the interplay between finite geometry and algebraic graph theory. And we have some other topics that will be covered. Annalena Horleman-Trautmann will talk about code-based cryptography, and John Sheekey will talk about tensors, semi-fields, Segre-Veronese varieties. So if you're interested, you can go to the website summerschool.finning.org to find some more information. Okay, so that's all that I wanted to say today.
Thank you for the talk. Okay, so any question for Sam?
So at the end, you explained sort of how you didn't have this connection between the dominating set, which is sort of how you got into this. But for the if the design isn't symmetric, but is there still some interesting structure that you think would be worth studying even without that connection, or not?
What do you mean is to study the structure without its you mean study the question of incidence-free pairs in this incidence structure without its connection to the edge domination number? Or...
Yeah, basically.
Yeah, I think this is a very interesting problem. I mean, we're not the first one to study large sets of points and blocks with no incidences between them. I guess the other papers which study those have less of an emphasis that these sets are of the same size. But there's, for example, a paper by Stefan de Winter, Jeroen Schillewaard, and Jacques Verstraeten, where they already studied this problem, because I would say it's quite interesting from a finite geometry point of view. So also in these other incidence structures, I think it's still a nice problem, worthwhile to study. Yeah.
All right, thank you.
Any other question for Sam?
Not so much a question, more a suggestion of where to look next. So the incidence graphs of symmetric designs are precisely the bipartite distance regular graphs of diameter 3. So the next place to look might be bipartite distance regular graphs of diameter 4, because there is a class of geometry/designs which these correspond to. So maybe that might be, if somebody's looking for somewhere to try this, that might be the place to try.
And which, you know exactly which these are the partial
So
geometries?
they go by different names. Variously known as symmetric nets, symmetric transversal designs, and sometimes as resolvable transversal designs. But that's a bit of a misnomer because there are other resolvable transversal designs which don't have this property. So
yeah. Okay, that's interesting because I was thinking if you would do this somewhere else, you look at the generalized quadrangles of order QQ or something. These are also quite natural things to look at, or other partial geometries or generalized polygons and so on. But maybe I should look indeed into these generalizations where you take the diameter 4. Now, interesting.
So the classic example is the bi-affine plane. So where you take an affine plane and delete a parallel class of lines.